the trapezoid rule is going to be similar, except that instead of having rectangular regions, we will have trapezoidal regions. So if I'm trying to evaluate a definite integral of f of x from a to b, I'm going to have some curve that represents my f of x function, and I'm going to have some boundary points, a and b, and again trying to find the area under the curve. So I'm going to take my interval from a to b and I'm going to divide it into n equally spaced subintervals. But you're going to see that when I create these subinterval geometric shapes, that I'm going to get a trapezoid in each one with the trapezoid rule. So what's going to happen is that I'm going to look at the y value that corresponds to a on the x-axis. And that's going to give me some length. And then if I look at x sub 1, which is the next grid point in my subinterval, and I find its corresponding y value, what I can do is I can connect those with a straight line. And again, it doesn't form this perfectly perpendicular line like it does with a rectangle, but because it's got some angle to it, some slant to it, it creates this trapezoid. And so if I redraw that trapezoid here with a little bit of an exaggerated slant, you can see that this length along the left comes from f of a, and this length along the right comes from f of x sub 1. And it's unusual to see a trapezoid drawn like this. If you don't mind, for a second here, I'm just going to rotate my entire page, because usually this is the way that we see a trapezoid drawn. This is our typical visualization of a trapezoid, keeping in mind that I sketched it freehand and that's supposed to be a right angle. So this length right here is actually the height of our trapezoid, and then these two here are those parallel non-equal bases. So if I flip this picture right side up, the length that's on the bottom is actually the height of our trapezoid. Even though it's along the bottom, it seems like it should be the base. But remember, your bases, base 1 and base 2, have to be parallel lines. And so these vertical f of x values will always represent our bases, and then delta x, these spaces between the subintervals, will actually be the height of our trapezoid. So let me run through the steps the same way I did with the midpoint rule. If I'm doing a trapezoid rule, I still need to know what delta x is. If I'm taking my interval from a to b and dividing it up into n equally spaced subintervals, then I still need to know delta x, which is what is the length of each of those subintervals. Remember, that tells you the height of each of your trapezoids. Alright, so then I can figure out what my subintervals are. Just like in the midpoint rule, once I know my delta x, whoops, that should just be an x. Sorry about that. Once I know my delta x, I can figure out my subintervals, and I have n number of them. And those subinterval endpoints are going to be the values that you actually plug into your given function in order to get those bases, the length of all your bases. So you're going to find the bases, or the length of all the bases, by evaluating your function at each one of those subinterval endpoints. Remember, when you're finding the area of a trapezoid, it's 1/2 the height times the sum of the two bases. That's just from geometry. And so now that I know the height of every trapezoid, and then in step 3 I found the base length of every trapezoid, or plural, each base, 2 bases for every trapezoid. Now I'm going to calculate and sum those trapezoid areas. And what happens here is quite interesting. What you're going to notice is that in every single trapezoid, you're going to be doing 1/2 times the height. And because the height is represented by our delta x, and we have equally spaced subintervals, the height is going to be the same for every single trapezoid. So this 1/2 delta x can be factored out, again, because it exists in the area formula for every single trapezoid that we create. So all we have to do is sum the base, or sum the 2 bases for each trapezoid, and then repeat that n number of times for every trapezoid we have. So let's look at how we would calculate those bases. So for the first trapezoid we have, the left base is found by doing f of a, and I'm going to add that to the right base, which is f of x sub 1. Look at what happens when I do my next trapezoid. Look at how you'd calculate the base length of each one of those. Well, the left base of this trapezoid is f of x plus 1 again. And then the right base is f of x sub 2. If I look at a third trapezoid, I'm doing f of x sub 2 again, and then f of x sub 3. Continuing on the pattern, it looks like for all of these inner bases, since they border 2 different trapezoids, they all get counted twice. And then our endpoints, A and B, they only border 1 trapezoid, so they only get counted once. Oops. Okay, so this is kind of sloppy. Let me rewrite it in a more clear way. So we have 1/2 delta x, half the height. I've got my leftmost base that I only count once. I've got 2 times f of x plus f of x sub 1, 2 times f of x sub 2, 2 times f of x sub 3, on and on and on and on and on. The pattern of multiplying all the inner bases by 2 continues until I get to my right endpoint, which is just counted once. So that's kind of the shortcut pattern that we can use here. Again, the leftmost and rightmost endpoints are counted once, and then everything in the middle is counted twice. From here, we're going to bring this discussion into error. So if these are approximations of our given definite integral, how good of an approximation are they? And that's where calculating our errors might help. So we're going to look at 2 formulas. We've got the formula for absolute error, and we've got the formula for relative error. absolute error, basically all we want to know here is, in its positive form, so regardless of whether we were overestimating or underestimating, how far were we from the actual answer? So here we see a C, and C is going to represent the calculated numerical approximation. Whereas X is going to be our exact answer that we would find using analytical techniques of integration. So basically we're just subtracting and taking the positive version of that answer. So how many units are we away from the exact result that we would get from using our integration techniques? Relative error looks at more than that. It looks at how many spaces are we away from the exact answer relative to what the exact answer is. So in other words, if I do some integration techniques analytically and I come up with an answer of 1, the area under the curve is 1. But then let's say I do a trapezoid rule and I get an answer of 10. Well, I'm only 9 spaces away from the answer, so my absolute error would be 9. But relatively speaking, that's a lot compared to what the actual answer is. You're actually 10 times larger in your approximation than you are in your actual answer. But if I'm talking about something in the thousands and I'm 9 units away from my answer, well, compared to the answer being in the thousands, that's not that bad. So relative error tells us a lot more in terms of how bad our approximation is or how good our approximation is, how far we are off from the true answer. You're going to see the relative error tells us more information about that compared to the absolute error.